So the purpose of this lesson is to talk about and to define this concept of the concavity of a function. And I know concavity is something you may have heard about in a science class, but we're looking at in a mathematical sense. So there are going to be two terms that we're going to be looking at in this lesson. They're going to be concave up and concave down. Right? So what does it mean if f is concave up? Well, what it means about the graph of f is it means that the graph is going to look like a smiley face graph, or the left half of a smiley face or the right half of a smiley face. Like a concave up graph always looks like that. Now there are two other statements that are identical to this idea of it being concave up. One of them is that the function is concave up. It means that the derivative is increasing. In other words, if you look at a picture of the derivative, that derivative graph will be increasing. And I kind of want to convince you of this, right? So suppose you're looking at this function here, right? Imagine with me for a minute, as we read it from left to right, what are these slopes? This slope is like -3, -2, -1, 0, 1, 2, 3. I think we would argue that all of those slopes are increasing. Not getting steeper, but increasing. And that's what I'm saying here. Saying that a function is concave up is saying the same thing as that the derivative of the function is increasing. But that's the same as saying that the second derivative is positive. And that shouldn't be surprising. We talked about that in the previous lesson, right? If a function is increasing, it means its derivative is positive. So we're now adding one level to that. If the function is concave up, the derivative will be increasing, and the second derivative will be positive. In this lesson, I'm going to be looking at graphs of all of these things, so we'll look at those in just a second. So now, what about concave down? If f is concave down, no, we don't use convex. Concave down means you've either got a sad face graph, or you've got the left half of a sad face, or the right half of a sad face. All three of those graphs there are graphs that are concave down. They're sort of opening downward, right? You can sort of see the space that's opening in a downward sense, whereas all of these are opening in an upward direction, right? Saying that a function is concave down is the same as saying that its derivative is, and hopefully you've guessed, is decreasing. And that means the same thing as saying that the second derivative is negative. Right? And again, I mean, pick one of these random graphs and take a look at it. This slope here is 3, then 2, then 1, then a half. Those slopes are decreasing. Note here it says that the derivative is decreasing. Even over here, this is 0, -1, -2, -3, -4. I understand those are getting steeper, but the derivative, the slope, is decreasing in those cases. I've now got 3 examples that all use different functions to sort of explore this idea, so we're going to look at those next. So here we go. I'm giving you a graph of the original function. So this is f. This is f. I want us to find the x values of any points of inflection and the open intervals where the function is concave up or concave down. Something I didn't mention on the previous slide is what a point of inflection is. A point of inflection is basically a point where concavity changes. Point where concavity changes. And so I'm going to use green here or I guess red for the concave down. I suppose I'm hoping that you're seeing like this is all a sad face graph. Sad face, sad face, sad face. And then somewhere in here, I'm not exactly sure where, that's not our job right now, but somewhere in here, it turns into a happy face graph. And so the idea is our point of inflection is what was this point where it changed from being concave down to concave up. Right. Note here I'm also asking only for the x values. So the x value of my point of inflection here seems to be about x equals, I don't know, 0.6. I'm just looking for what, roughly what this value was where it changed. Where is this function concave down? Well, it seems to be concave down from negative infinity all the way over to this 0.6. So concave down, I should use the appropriate color, it's concave down between negative infinity and 0.6. What about where is this thing concave up? Well, it should be concave up wherever we've got the happy face graph. This seems to be from 0.6 over toward infinity. And so I'm really hoping that when you see these intervals, they're reminding you, sorry, I just can't get that decimal point right, they're reminding you of the intervals we saw in the first derivative test. The next video in the sequence is about the test for concavity, which is really, really similar to the first derivative test. But this is us looking at the original function. We're going to go on and look at another example that's a little bit different. So in this problem, I have the graph of the derivative of a function. So this time I have the derivative, not the original function itself. And same thing, I want the x values of points of inflection and the intervals where the function is concave up or concave down. I want to begin with, what does it mean for f to be concave up? On the first slide here, I gave something that was the same as. Saying that f is concave up is the same as saying that the derivative is increasing. Well, you're in luck. This is a picture of the derivative. So where is this picture increasing? This picture is increasing right here. Seems like it's on the interval from 2 to infinity. So great, that's where our function is concave up. It's concave up wherever the derivative is increasing. That means between 2 and infinity. Similarly, where is f concave down? Well, again, f being concave down is exactly the same thing as saying that the derivative is decreasing. I shouldn't need to say it again, but I will. This is a picture of the derivative. I've already got the derivative. So where is this thing decreasing? It's decreasing right here. Remember that when I talk about an increase and decrease, I'm always reading from left to right. So this one is decreasing, this one is increasing. So great, this function seems to be decreasing on the interval between negative infinity and 2. And so my last question is going to be, what about that point of inflection? We'll have a point of inflection at 2, and some of you may want to say that the point of inflection will be 2, negative 3. That's not true, because this is a point on the original f of x graph, and this isn't the original f of x graph. All I know is this is 2, whatever I get by plugging 2 back into the original function, right? Note that this is an interval, this is an interval, this is actually a point, right? So even though they look similar, this is the point of inflection. This is the point where it changes from being concave up to concave down. Got one last example. And in this example, I'm now looking at the second derivative. I'm saying this is a graph of the second derivative. I want to know the x values of the points of inflection and the open intervals of concave up and concave down. I'm going to do the same thing I did before, right? I want to know where f is concave up. Sorry about that O. Well, what does it mean for f to be concave up? It means the derivative is increasing. That was really helpful on the last problem because I had a graph of the derivative, but I don't have that this time. It also means that the second derivative is positive. Well, we're in luck. This is a graph of the second derivative. Where is this graph positive? It's positive right here. So my function must be concave up between negative 3 and 2. Right? If you haven't already done so, pause the video and do this for yourself for concave down. Where is the original function concave down? I'm assuming that you've paused it and tried it on your own. That's where the first derivative is decreasing, and it's where the second derivative is negative. I don't care about where the first derivative is decreasing. Where is the second derivative negative? This is all under the y-axis. This is all under the y-axis. And so this seems to be from negative infinity to negative 3, and from 2 to positive infinity. The final question left to answer is, what are the x coordinates of the points of inflection? Well, concavity changed right there and right there. That was -3 and +2. That means my points of inflection will be -3 comma something and 2 comma something, because in both of those places concavity changed. I hope that sort of makes sense. I hope you have some idea of what concavity is and what it looks like. What it looks like for the original function, what it looks like for the first derivative, and what it looks like for the second derivative. That's what we're looking at here. In the next video, I'm going to talk about how we do all of this analytically, like how we work with functions. So I will see you in that video.